Hello, my name is Alfredo Hernandez. I'm a senior student at Sulross State University, and I'm going to present you a program that I created, which is going to have 5 solutions for 5 problems from this book, Appendix B. Here I'm going to click the icon of my program. It's going to open, and this is problem number 3 that says it is striking that 145 equals 1 factorial plus 4 factorial plus 5 factorial, and the only other integers satisfying that are 1, 2, and 40,585. And then it's asking the question, does d1 times d2 all the way up to dk ever equal to the sum of 2 to the power of d, and depending on the value of k is gonna sum that number. If k is 5, it's gonna sum 2 to the 5 times, and if it is 6, it's gonna sum it 6 times, and same for the other. For 3 to the d, depending on the value of k, it's gonna sum that one. And it's asking whether that is equal to d1, d2, all the way up to dk. I'm gonna continue. Next, here is my problem 3. So here I'm gonna write 50, and it's gonna, after I run the program, it's gonna show 2 values. So from n1 all the way up to n50, it is showing me these 2 results. And if I go to 200, it's going to show me that our result, which is 145, which is equal to factorial 1 plus factorial 4 plus factorial 5. And if I go to 50,000, it's going to show me the result, which this equals 4 factorial plus 0 factorial plus 5 factorial plus a factorial plus 5 factorial. I forgot to add the plus symbols, but that's what it means. And for this other part, I'm gonna write 10 to the power of 2. This is gonna compare d1 all the way up to dk. The multiplication of that is gonna say if the result is equals to 2 to the d, I think, yeah, 2 to the 10, and it's gonna be sum 10 times. So after I click check, it's gonna say no, that there are no results. And if I change that to 3, no, there are no results. I can write 20. It's gonna give me nothing, and I can continue, but it's probably gonna say no. Try 15, and this is running in the background, and it says no. So that's the answer for the second question of the problem. I'm going to continue to the next problem. Problem number 7. It says that an integer n is semi-perfect if n is a sum of distinct proper divisors of n. Just, I want to point out that it says that an integer n is semi-perfect if n is the sum of some proper divisors of n. It doesn't have to be all of them. And here's giving me an example. 104 equals 2 to the third times 13, which is semi-perfect because 104 equals to this sum. And then it's asking, well, it's saying a semi-perfect integer is irreducible if it is not the multiple of a smaller semi-perfect number. For the first part, I could write a program for that, but for the second part, I couldn't do that. It was a bit hard, so I'm just gonna show the part where it talks about semi-perfect numbers. Here, I'm gonna insert 100, and this is gonna show, the program is gonna show me from values from 1 to 100 what values are semi-perfect. Here is showing me all these numbers that are semi-perfect. I can go all the way up to 1,000 and change that to 5,000, why not? And it's showing me all these values. I'm gonna change that to 20,000. And I can continue go on and on. 100,000. This is gonna take a little bit because it is processing all those numbers. Yeah, it's taking a bit of time. It is continue processing that. I'm just gonna wait a few seconds more. And there it is. Yep, it only shows a few more. And this is for this program. It is only going to show semi-perfect numbers for this problem 7. I'm going to continue to the next problem. It's problem number 8. It says the equation 1 plus 2 plus 3 all the way up to n equals 1 squared plus 2 squared plus all the way up to k squared has just 4 solutions, 3 being 1 and 1, the second being 10 and 5, and 13 and 6. Find the fourth solution that is less than 1,000. And it is asking if I can change the powers. So it can either be to the power of 1, 2, 3, 4, and I can compare that to a different power, like, I don't know, whatever I want. So I'm going to continue next. And here, I'm just going to check the first 100 values to the power of 1 is the first one, and the second one is the power of 2. This is going to go from 1 all the way up to 100. It's going to compare all those values. So it's like whenever n is equals 1 and all those values that are, I think is compared to 1 from 1 to 100k, and it's showing me this. So if I change that to 1,000, I think it's gonna show me the fourth case that I'm supposed to find. But this is gonna take a little bit because it's using a lot of processing. So we already know these 3 values. These are the ones that the book talk about. And I just need to find the fourth one. Yeah, it's gonna take a few more seconds. It's loading. And there it is. So the fourth value is 645 raised to the first power which is equals 208,335, which equals to 1 square plus 2 square all the way up to 85 square. That's the fourth value. And I can continue to check more problems, but that will take more time. Next problem is number 12, which is asking generalize Wilson's theorem by looking at the values, and it's showing me 2 prime 2 to a value prime minus 1, and there's going to be a number, and the factorial of that number is going to be applied mode in the same prime number to square, and then it's going to show me a different result where the only number that changes is 3, which is, this is going to be a, and p to the third, and then fourth is going to be multiplying p and p to the fourth power, and so on and so on. For that, I'm going to use a lot of a values, and I can choose any prime number I want. So here I'm gonna write 100, and it's gonna show me all these crazy results. This means that it's gonna start when a is equals to, and for the prime it's gonna choose 3, and it's gonna go all the way up to 99. These non-values, it means error, that the number is way too big to calculate, and I can change the prime. It's gonna show different results. I can choose 11. So when I write a composite number, it's gonna give me all zeros. I can choose 12 too. Oh, apparently with 12 it won't give me zeros, it gives a different result. Let's see, 24, 28, let's see, 6, and I'm gonna choose 13. I'm supposed to compare these results and create a general equation for that, but since I'm just doing the computer part and show that it works. Oh, that's 50,000. That's gonna take a while. Since it's gonna take a while, I'm just gonna crash my program, and I'm gonna open it up again and go back to 12. This is where I was. Now I'm just gonna show you the last problem, which is problem 20. There are many more n such that dn equals dn plus 1. This means the divisors of a number n equals the divisors to n plus 1, the divisors of n plus 1, and in fact triplets are common, the first being 33, 34, and 35 equals 4. It will be interesting to know where the first quadruplet, quintuplet were. And let's see, I'm going to calculate the numbers from 1 to 10, and that's going to show me one twin, well, I mean 2 twins. So when n is equals 2, it shows that this results in 2. It has two divisors, and 2 plus 1, which is 3, has 2 divisors as well. And if I go all the way up to 50, it's gonna show me the first triplets, which is when D is 33 and D 34 equals 4 and 35 equals 4 as well. Now I'm gonna try to find the first quadruplet. I'm gonna go all the way up to 200. It doesn't show any quadruplets just yet. I'm gonna go all the way up to 500, and there it is. It's gonna show me the first quadruplet when when n is 242. The divisors are 6. It's gonna it's showing me that all the divisors are 6, and now I have to find the first quintuplet. That is gonna be a little bit more hard, so I'm gonna write 30,000. Yeah, 30,000, and check where the quintuplet is. This is gonna take a little bit. Yep, it's gonna take a little bit. Yeah, it's still loading. It's gonna take a few more seconds because it is a big value. I'm just gonna wait a little bit more. And there it is. So I'm gonna scroll down until I find the first quintuplet. More quadruplets. Another quadruplet. Another quadruplet. And here it is. The first quintuplet is when n equals 11,605, and it has, all of them have 8 divisors each. This is the first quintuplet, and I can continue, and it's going to show me more twins, triplets, and quadruplets and quintuplets. And that's the 5th problem, and this is the end of my presentation. The code of this program is available in the description. The program is not downloadable just yet because I have to create another program to install this program, which I will do later. I hope you like the video, and thank you.